when potential is greater than E.
Again, in the classically forbidden region, wave functions or Schrodinger equation solutions are exponential, real wave function. I mean, maybe multiplicative constant may be imaginary, but functionality is real actually, isn't it? So in that case, you will not have any current density. J will be 0, isn't it? That's the observation. Give me a minute. So let me take one simple, some arbitrary potential, okay, like this. Suppose V of x as a function of x here, okay? Some arbitrary potential. And again, our energy should be greater than V minimum, classically or quantum mechanical, okay? That part is always true. Is that okay? Energy should be greater than V minimum, okay? Let me take some energy value E here, okay? So now look at here, classically what would happen? Classically what would happen? Let me take this one as x1, this one as x2. It need not be symmetric, okay? Classically what would happen? Particle, again, if particle is given this much energy in this kind of potential, particle will oscillate between x1 and x2, am I right? If you drag the particle and if you leave here, again, so its kinetic energy is 0 here, it will try to go to minima. Again, from there, again, it will go to other extreme position and it will oscillate. Okay, need not be simple harmonic oscillation, but it will oscillate between these 2 points. It will never go outside, am I right? Classically. Because if it goes outside, in that region, your potential energy is higher than the energy. So what is kinetic energy? Energy minus V, isn't it? If potential energy is higher than the energy, kinetic energy is negative. That will never happen classically, okay? So now look at here, we call this one as classically allowed region. Allowed region, CA. So can I say like this? Classically allowed region. So this region, we call this one as classically forbidden region. Can I call it as CF? This is also CF. Is that okay? Classically allowed region means your kinetic energy is positive. Everything is fine. Okay? And classically particle is bound here. Can I say like this? Particle is bound within x1 and x2. It cannot escape, isn't it? Potential is going to infinity. Can you observe this one? V of x is going to infinity as x tends to plus infinity or minus infinity. V of x is going to infinity. Okay? So observe this one carefully. Particle, classically, particle is bound in this region. Particle cannot escape in any side, either positive x-axis or negative x-axis. Particle cannot escape in this region or in this region. Am I right? As well as particle can be there only in this region, isn't it? Now observe quantum mechanically. Quantum mechanically, look at here. Let the best example, best similar example we have already studied. Am I right? That is half m omega square x square. Am I right? Isn't it? In that case also observe everything. Okay. So find the similarity. In that case, look at here. These are classic. Again, look at here. We call them as classical turning point. I just forgot. Okay. This one and this one. Okay. Classical turning point. That means, so particle come here and it will turn back. Am I right? Particle will come up to this position and it will change its direction of motion, isn't it? So now look at here. These two are called as classical turning point because classically particle will come up to here and it will turn back literally. So then again particle can come up to here. It will turn back actually, isn't it? Now again here also you can say this is some x1 and x2. Okay, classical turning point only. Okay, but look at here, our particle can exist outside this region also. Am I right? We have seen our psi naught. Suppose if we take particle is in the ground state, isn't it? We have seen our Gaussian wave function. Suppose if this is x1 and x2. So compare classical and quantum, okay? You can find particle outside this classically allowed region also. You can find again stuck. Why? So what I am saying is, so take quantum harmonic oscillator, that's the example, similar example, okay, similar potential. But here I'm trying to generalize this one, okay. So now quantum mechanically what happened, you just observe that one, okay. I mean, so particle can exist outside this region also, but your J was 0 here, isn't it? Particle cannot escape in any of this region. Particle cannot escape, that's what I said. J is 0, okay. It's not a what you call free flow of particle in any of positive x-axis or negative x-axis, isn't it? Observe that fact. So even though particle exists outside this region, your probability of finding the particle is decreasing in this region. You can observe, am I right? It's a decreasing function. It will be 0 at infinity. Particle cannot escape to infinity because your wave function is 0 at infinity, isn't it? And J equal to 0. There is no free flow of the particle. So that's why quantum mechanically also this is a bound state. We say that one as a bound state. Speak out. Is that okay?
Sir,
Yeah.
sir, when x becomes 0, then some probability will be there.
Yeah, probability is there. Mod psi square is there. You have distribution. Why that question comes? No, yeah, at infinity, I am talking about decreasing to 0. At x tends to minus infinity, it is 0, Gaussian. As x tends to plus or minus infinity, this whole thing is 0, isn't it? That means as well as J equal to 0. So in this situation, what I am saying is, whatever the energy you take, okay, what the same, again, suppose even if you take first exact state, am I right? What is mod psi square? It will be like this kind of function, am I right? Isn't it? So J equal to 0 again in this situation also. So that's why particle, so one is current density is 0. Current density 0 says that particle cannot freely move, isn't it? It's not a free flow of particle, one thing. And other one is, so our probability density is 0 at infinity says that particle cannot escape to infinity. It is stuck in this region. Okay? So that's why whatever the energies you take, again, for ground state, first exact state, the same situation. That's why, so it will allow only bound state, always bound state, isn't it? Quantum mechanically also, this kind of potential will allow only bound state, whatever energy you take. But quantum mechanically, what can happen is, particle can exist. There is a finite probability of finding the particle in this region. So this whole potential, okay, so this is classical bound state as well as quantum mechanical bound state. This will allow only bound state, classically as well as quantum mechanical. But find the difference between classical bound state and quantum mechanical bound state. In the classical bound state, look at here, particle cannot exist here. But in the quantum mechanical bound state, you have finite probability of finding the particle in these regions. But particle will not escape. Yes?
The current density will be 0 in classical allowed region.
No, classically we don't define current density. It's 0 only. You can say it is 0 because it cannot escape, isn't it? No, classically we don't define probability current density. Okay? Yeah, that's quantum mechanical idea. Now, what I am saying is, so again, I hope you got this classical turning point, classically allowed, classically forbidden. I hope you know all of this point. So this kind of potential, so this is classical, this will allow classical bound state. And this will allow quantum mechanical bound state. It will allow only bound states. But quantum mechanical bound state, particle can exist outside the classically allowed region. That's the only difference. But particle will not escape out to infinity in any of these cases. Okay?
So Sir, why we are saying x1 and x2 is classically non-point there, quantum angle?
No, I mean, we are just comparing it with classical. If it were classical, these particles should have turned back, isn't it? We are just observing that one, that's it, okay? So this is classically allowed region, and our particle can exist outside that region also. To observe that one, I have just pointed out classical turning point in that curve also, okay?
Sir, how possible
Huh?
quantum mechanics a particle is the flow on?
Wait, how?
How possible, sir? Because the particle has no energy, then he remove forbidden region. How, sir?
No, that is non-classical effects. A lot of things happen that we don't know how, isn't it? How particle can move to classically forbidden region where our kinetic energy would be negative, am I right? That what Schrodinger equation told us. That's what we can say. Is that okay? Speak out. But remember, both are called as bound state because particle cannot escape to infinity in any side, either positive x direction or negative x direction, okay? No, J will be 0 everywhere, okay? J will be 0 either you take in this region, the functionality is same, right? J is 0 everywhere, whether you take any of this region, okay? Yeah, observe that fact. So next one, let me take some other kind of potential. So whatever the energy you take, so classically that will be bound state, quantum mechanically also that is a bound state, okay, in this kind of potential. Now let me take some other type of potential. V of x as a function of x. It is going to infinity here, okay. Can you see this one? It is going to infinity. Now let me take two situations. One situation is energy E1 here. And I call this one as some x0. Classical turning point again, okay. Now you have two options here. You can put particle here with this energy and you can leave the particle. What it will do, it will slide off, am I right? So if you leave the particle here with this potential, it will go out to minus infinity. Or if you shoot the particle from this side towards this kind of potential with this much energy, what will happen? Particle will come up to here. So classically, okay, I'm talking classically. If you shoot the particle from negative x direction, so towards positive x direction, so into this potential with this energy, okay, with this much energy, particle will come up to this point and again it will go back. And if you leave the particle here, then also it will go to infinity, isn't it? Classically, this is a scattering state, am I right? E1. So classically, this is a scattering state, isn't it? Are you getting my point? So what is quantum mechanical idea? Okay. So our Schrodinger equation says when energy is greater than the potential energy, am I right? In this region, isn't it? So in that case, look at here. Have you seen our solution? E power ikx kind of solution, isn't it? So that's why quantum mechanically also, so you will have some current density. Particle can escape out to minus infinity. Particle cannot escape here because this is the region E less than V. This is the region E greater than V. Isn't it? In this region, okay, you will have e power ikx kind of solution of the Schrodinger equation, which will have some current density, and particle can escape in this region, quantum mechanically also. Quantum mechanically, particle may exist in this region, but it cannot escape. Why? If E is less than V, your solution is e power kappa x kind of thing, am I right? E power plus kappa x or e power minus kappa x, observe mathematically, okay? So in classically forbidden region, particle cannot escape. I mean, so this whole region is classically forbidden, am I right? From x0 to plus infinity, the whole region is classically forbidden region. Particle cannot escape there because you will have this kind of solution whose current density is 0, isn't it? So, but in this region, you will have this kind of solution, e power I kx kind of solution. So that's why particle can escape here, classically as well as quantum mechanically. Yes.
Sir, quantum mechanically particle also cannot escape here, sir, whenever E less than B, sir.
Quantum mechanically, particle can exist here, wave function can exist here. I told like that. But current density is 0 only.
The current density 0 means that the
Particle cannot flow to infinity.
flow to infinity. Okay.
That's why. But particle is not bound here, isn't it? We say, so this will allow again, so E1, it's a classical scattering state. Okay, and quantum mechanical, also quantum mechanical scattering state. E1 is both classical as well as quantum mechanical scattering state. Scattered, I mean, it is not bound. Scattering means it is not bound. It can go to infinity. It will escape to infinity. Is that okay? It will escape to infinity. It can escape only in negative x direction. That's what you need to observe. In the positive x direction, you will not have any current density. Is that okay? After x naught, you will not have any j. Okay? So, but in the negative x direction, it can escape because it is going 0 somewhere here. Okay? X naught is classical turning point.
There is no quantum turning.
No, there is no quantum mechanically. We don't define turning point. Okay, you can call it as classical turning point. This is also classical turning point because classically particle can come up to here and it can go back, isn't it? Now look at here. I'll take another energy here. Okay, the similar potential. Again, it is going to infinity. I'll take one more energy, E here. Okay. And what I do here is, let me first discuss only this region. Let me first discuss this region. Okay. Now look at here. If you shoot the particle, so classically, if you shoot the particle from minus infinity towards this one, what will happen? Particle can come up to here and it will go back. It will not go here at all. If you shoot the particle with this energy, okay, from negative x, okay, particle can come up to here and it will go back, isn't it? This is one of the turning point, x1, x2, x3. But if you keep particle here somewhere, okay, if you leave particle here with this energy, then what will happen? Particle will be bound. It will oscillate between x2 and x3, isn't it? Classically bound state, am I right? Here is a classical bound state. Okay, but if you shoot particle here, that is classical scattering state. Because here particle is bound classically between x2 and x3. But here, if you shoot the particle, it will go back, it will escape out to infinity again. It will come up to this point and it will escape. It will never come to this region, isn't it? Classically. This is a classic, again, if you start here, or if you shoot here, in this region, that's a scattering state only. But if you start here, it will be bound. Particle will not escape. It will be bound between x2 and x3. Classically, okay? Now we shall see what would happen quantum mechanically. Okay, obvious one. I think classically, I think you don't have much problem, isn't it? To say whether it is a bound state or scattering state. Isn't it? It should be obvious fact for you. Whether particle escapes or not, that will decide whether it is scattering state or bound state, isn't it? Particle will not escape. Now we shall concentrate on this region, okay? If you leave particle here, okay, quantum mechanically, particle can come here also. Is that okay? Once a particle comes here, it can escape in this region where your energy is greater than V, isn't it? Are you getting my point? So again, if you talk only about this region or this region, in this region it cannot escape. Why? Your energy is less than V, am I right? In this region it cannot escape. Your potential is keep on increasing. But what will happen is quantum mechanically, if you leave particle here with this energy E, okay, it may go in this region also. You can call it as a tunneling. We call that as quantum mechanical tunneling sometimes, okay? Yeah, what will happen is you will have I'll talk not current density. Current density, you can't define current. You can define current density maybe here or here. You can't define current density. Okay. What I'm saying is particle can go here. Once it goes here, your J will be non-zero. What I'm saying is quantum mechanically there is a possibility of if you leave particle here, okay, it can go into this region also. Once it goes here, it is free to escape to minus infinity. Look at this region, energy is greater than V, isn't it? That means quantum mechanically particle can escape, isn't it? To infinity. Even if you start here. Speak out. So that's why this is quantum mechanical scattering state. Quantum mechanical scattering state.
And sir, to what positive?
Wait a second. Suppose if particle, quantum mechanically, okay? Particle is shooted from minus infinity to toward this kind of potential, okay? So now particle can go back to infinity or particle can tunnel to this region. You are not seeing here. If particle, again it is there, okay? It is there in Jetile as well as Griffiths. If particle is shooted towards this region, this potential from minus infinity, particle can reflect back. Quantum mechanical I am talking about. Particle can reflect back as well as particle can tunnel into this region. Classically it will not tunnel, isn't it? Classically it cannot cross this barrier. This barrier height is more, isn't it, than the energy. If quantum mechanically, if particle is shooted from minus infinity with this energy, particle can reflect back as well as particle can tunnel into this region. Okay? Again, in the both cases, it is quantum mechanically, it's a scattering state. If you leave the particle here, so then also it can, escape this region and it can go to this region. Once it goes to this region, it is free to move to infinity. That means particle can escape. That's why it's not a bound state. Quantum mechanically, it's not a bound state. Quantum mechanically, again, either you start here or here, it is a scattering state only. Wait a second. And one more thing you need to observe. Classically, you will never find this. These are classically forbidden region. Am I right? You will never find particle here. But quantum mechanically, there will be probability of finding the particle here. We shall see later. Yeah. Now speak out.
Sir, in potential or infinity, the particle is allowed to find from the region.
No. Again, if potential is going to infinity, am I right? In this region, you will see later, you will have exponentially decaying solution. Okay, particle cannot escape in this region. Okay, probability of finding the particle at plus infinity, 0. It cannot escape. But probability of finding the particle at a minus infinity, that is non-zero. It can escape. Whether you start here or here.
But in potential wall, the big temples are not out of there.
In potential well. No, potential well also, isn't it? Our potential is infinity here, am I right? 0 here, A here. It is infinity. Particle is bound between 0 to A. It will not escape. Particle is trapped, isn't it? It will not escape. That is bound state. That is purely bound state, just like our harmonic oscillator. Is that okay? That's pure bound state. It will not allow any scattering state. But I'm not talking about that kind of what you call infinite potential, sudden infinite potential here. Here potential is slowly going to infinity. That's why you will see in this region your wave function should be e power minus kappa x kind of thing. It will be exponentially decaying. So it will have j equal to 0 also in this region. So particle cannot escape here, but particle can escape here, isn't it? In one side particle can escape, isn't it? Then it is scattering state.
So, sir, in this
But look at here, this region, if you start it here, okay, this is classical bound state. But this is quantum mechanical scattering state, because classically if you keep particle here, it will never escape, okay? But quantum mechanically if you keep particle here, it can escape to this one. We call that as tunneling. Okay, the best example is your alpha decay. Okay, so again this is nuclear radius. Okay, so inside the nucleus alpha particle will experience some negative potential, attractive potential, alpha particle. Okay, so when it comes outside it will experience 1 by r repulsive potential, electrostatic repulsive potential. When not Yukawa, you can take your what you call Coulombic potential. Okay, so when it just comes outside, so look at here, it will experience repulsive. Alpha particle is positive, nucleus is positive. When it is inside the nucleus, it will be in the negative potential. Okay, so this looks like this. Now alpha particle will have energy usually less than the energy of this barrier. Alpha particle, whatever inside the nucleus, it will have the energy less than the energy of this height, this barrier. You can call it as a barrier. But still you will have alpha decay. We call that as quantum mechanical tunneling. Classically, if alpha particle have got this much energy inside the nucleus, it should not come out, isn't it? If its energy is less than the barrier height, it should not come out, isn't it? Classically. But again, we will have alpha particle decay, isn't it? We have practical example where alpha particle is found outside the nucleus, isn't it? Even though its energy is less than this barrier. Once alpha particle is found here, its energy is E only, remember. You found alpha particle outside the nucleus whose energy is less than the height of the barrier. How it came outside, isn't it? The same thing can happen here, okay? That's why these kind of states are quantum mechanically scattering state, because particle can escape in one of the region, okay? If particle escape in any one of the region, then that is scattering state, okay? Let me take one more very simple one. Suppose if I have this kind of situation, okay? V of x is like this. Suppose if you have energy greater than this one, okay, E1. If you have energy E1, speak out. Now in this case, look at here. Classically, if you shoot the particle, again particle will come. It may slow down here, okay? It may slow down here. Again, it will move out to positive infinity. Or if you shoot a particle from what you call negative, some plus infinity, so towards this one, is this a kind of barrier? Can I say like this? Now, if your energy is higher than the barrier, then definitely you will have particle will not stop, isn't it? Classically, if you shoot the particle either from this direction or from that direction, you will have 100% transmission, no reflection at all. Okay, quantum mechanically also, if you shoot the particle either from here or here, it will escape only, isn't it? Because energy is greater than V, isn't it? That's why J will be non-zero. Okay, you will have some free flow. But quantum mechanically, what will happen is, if you shoot the particle from here, some reflection coefficient exists that we can't imagine classically. Classically, if you shoot the particle with this energy, so particle energy is higher than the barrier, isn't it? It should go 100% transmission classically, but quantum mechanically not 100% transmission, some reflection will also be there actually. But quantum mechanically as well as classical, this is a scattering state. QM and classical mechanics, scattering state. Okay, but you should know the difference. Okay, both will not give the same result. Okay, it will have some reflection coefficient quantum mechanically. If you shoot the particle either from here or here, so some particle may reflect, but classically no particle will reflect. Okay, but if energy is like this, in that case also, look at here, if you shoot the particle, okay, so see this one, in that case also, quantum mechanically as well as classical mechanically, this is scattering state only, because particle can escape here. Okay, now but what will happen classically, look at here, it is there in the book. Okay, if you shoot the particle from minus infinity to towards this one, classically particle will come up to here and it will go back, 100% reflection. But quantum mechanically, if you shoot the particle from minus infinity, what will happen is some particle will reflect, some particle will tunnel and go to this region, and there they will escape. But somehow particles are escaping here. That's why it's not bound state. Quantum mechanically, it's a scattering state. But what is happening apart from classical things? That is, so if you shoot the particle from this side with this energy E2, okay, classically it should have gone back, isn't it? Classically 100% reflection. Okay, but quantum mechanically what may happen is tunneling can happen. Quantum mechanical tunneling. Some particle may tunnel and go to this region. Not 100% reflection. Okay, less than 100% reflection. Little bit transmission will be there. And once it goes to region, again it will escape to plus infinity. The same thing will happen if you shoot the particle in this side. Is that okay? So, but particle is escaping, it is not bound in any situation. Maybe it may tunnel, okay, but it is escaping. Am I right? So that's why. So we call that one a scattering state. Quantum mechanically also it's a scattering state. Is that okay? Now, what is tunneling? The best way to define tunneling is, it's a process that a particle goes from one classically allowed region to an other classically allowed region. You will have finite probability of finding the particle here also, okay? But if you find particle here, we don't call it as tunneling. If particle shooted in this direction, if it found in this direction, particle was shooted only in this direction. But if it found in this direction, we call it as tunneling. Process of going from one classically allowed region to other classically allowed region, crossing the region of classically forbidden region. Exactly the same thing is happening here, okay? Classical particle was in one classically allowed region, and it can go to other classically allowed region by crossing this classically forbidden region. We call that as tunneling. The process is tunneling.
So each all of the problem is there, right?
Yeah. Yes.
Sir, and sir, tunneling does not produce a quantum mechanically bound state, sir. It is that.
Yeah. So it is not bound state. I'm not saying it is bound state. It is scattering state also. But compare it with classical scattering state. Okay. What is extra thing that?
And sir, whenever potential touches to infinity, then the quantum mechanically bound state will produce, sir.
So here, potential is touching infinity. Will it produce quantum mechanical bound state? No. Yes. If particle can escape in any one of the region, then it is scattering state. Are you getting a point? So I'll come to that point. Wait for a bit. Here also particle cannot escape here, but particle can escape here. Am I right? If particle can escape in any one of the region, that is scattering state only. Quantum mechanically, okay? But here compare. Yes?
Then sir, it is not bound state. If particle is escaping
in any one of the region, then it is not bound state, it is scattering state.
Okay, sir.
Yeah. Now what I am saying here is, again, this is scattering state, no doubt. Quantum mechanically is also scattering state, but find the difference between classical phenomena and quantum mechanical phenomena, okay? If particle goes from one classically allowed region to other classical allowed region, okay, by crossing some classical forbidden region, you can call that process as tunneling. Okay. Now I'll take this situation. Is that okay? Now let me come to this one. Okay. In one region our potential is going to infinity. In other region also our potential is going to infinity. Isn't it? Particle cannot escape here. This is also classically forbidden region. This is also classically forbidden region. So that's why particle cannot escape in this region or in this region. J equal to 0 here. J equal to 0 here also. You will have real function actually. Okay. You can't have what you call free flow of particle. This will allow only bound state. So classical as well as quantum mechanical bound state. Whatever the energy you take. Okay. Whatever energy you take. Now I have one more example. You should read Jatili as well as Griffiths for this particular topic. Okay, I hope you got that point. This is V1, okay, V2 here, okay, as a function of x. Now look at here, let me take one situation, E1, okay, and let me take other situation, E2. So look at E1 situation, okay, if particle is again in this region, so in case of E1, okay, so classically it's a bound state, obviously, isn't it? Particle should be bound in this region, okay. Quantum mechanically, what is that one? Whether bound or unbound, quickly. If particle have got energy E1 in this kind of potential, okay, so this is our potential. This is our potential, okay. Speak out. If particle have got energy E1, whether it is bound or unbound, quantum mechanically, quickly tell me.
Some JM just get it.
How? Can particle escape? Where particle will escape? Remember, potential V at plus infinity, okay? If you go to plus infinity, potential is V2, okay? V at minus infinity. If you go to minus infinity, potential is V1, okay? It is attaining some constant value. How it is scattering state? Tell me.
It will be bound state.
Why not scattering state? Why not scattering state? First explain me.
Both the regions, the potential is greater than both the regions.
Here also, again, E1 is less than V. Here also, E1 is less than V. Throughout this region, This is also classically forbidden region. This is also classically forbidden region. Particle cannot escape here as well as here. Current density is 0. Speak out. Earlier potential was different. Look at here. It was some high, okay, and it went down, okay. It was some high value and then it went down. But here I have taken the situation where potential is approaching a constant, okay. Speak out. Find the difference. Okay. You are thinking like this. But it went to some height and it go down. You had classically allowed region here. tunneling can happen. But our potential in this situation, okay, it is approaching a constant value. At V at minus, if you go to minus infinity, it will be a value V1. Okay, our potential have got value V1. Is that okay?
Restricted. It is restricted to the minus infinity also.
Not restricted. Look at it. Potential is approaching a constant value. It is not decreasing. After some time, it's not decreasing, just like here. Is that okay? V at minus infinity equal to V1. Okay. Or as x tends to minus infinity, or V at minus infinity is equal to V1 only. Let me write like this. Okay. So that's why. So find the difference between this one and this one. Okay. So that's why E1 is the situation. E1 is a classical as well as quantum mechanical bound state. Why? Particle cannot escape in either of the direction. Is that okay? Particle cannot escape. Remember, this potential is not decreasing after this one. Okay, it is a constant value. Are you getting a point? So it was decreasing here. So this region was acted like a barrier, and it can tunnel and it can go to other region. Here there is no classically allowed region at all in minus infinity. In minus infinity region, in this negative region, there is no classically allowed region at all after this point. Is that okay? So there is no possibility of tunneling kind of thing. Okay? So that's why particle cannot escape here. Particle cannot escape here. That's why it is bound state. Okay? But what about E2? What about E2? Quantum mechanically? Scattering state. Why?
Because here E2 is greater than V1 in the left hand side.
Yeah. So now in the left hand side, E2 which is greater than V, you will have some J which is non-zero, probability current density. Particle can escape, but particle will not escape here. Why? In this region E2 less than V. Particle cannot escape here, but particle can escape in this region. Am I right? Isn't it? It's a free flowing particle in this region. Again, it may not escape to plus infinity, but it can escape to minus infinity, isn't it? So that's why particle can escape here, quantum mechanically as well as classically. It's a bound state. Okay? Scattering state. Quantum mechanically as well as classically, this is a scattering state. If particle is allowed to escape in any one of the region, it is scattering state. Is that okay? Yeah. If energy greater than V2, then also again, if energy greater than V2, so it will escape in this region as well as in this region. That's it. It is less than V2. Again, look at this one. Look at this region. This energy is greater than V1. E2 is greater than V1. So in this region, you will have J which is non-zero. Particle can escape here. I can write this one. If E is less than V at plus infinity, and is very important here. Okay? If energy of the particle is less than V at plus infinity, and as well as, okay, E is less than V at minus infinity. This situation or this situation, then it is quantum mechanically or classically bound state.
Bond state.
Okay, and should be there, okay, not or. Look at here. In this situation, E is less than V at n plus infinity, okay? E is less than V at plus infinity, but E is greater than V at minus infinity. It can escape to minus infinity. But this is scattering state. I am talking about this one, okay? If energy is less than potential at plus infinity as well as potential at minus infinity, then it cannot escape in any region, isn't it? Write down, it cannot escape. Isn't it? If energy is greater than V at plus infinity or energy is greater than V at minus infinity or both, okay, or both. Or both. So then it is scattering state. If energy is greater than V at plus infinity or V at minus infinity, it can escape. It can escape, isn't it? Don't forget this situation. This is very good example, okay? Isn't it? In this situation, energy less than V at plus infinity, but energy greater than V at minus infinity, isn't it? Look at here. Energy is greater than V at minus infinity, isn't it? Scattering state. If energy greater than V at plus infinity or any one, if energy greater than V at plus infinity or E at minus infinity or both, it can escape.
Once in scattering, there is scattering state.
It's a scattering state, always scattering state. Okay? It can escape, isn't it? Suppose if you take this situation, isn't it? If you have taken this situation, isn't it? If you take this energy, now energy less than energy greater than V at plus infinity as well as energy greater than V at minus infinity, am I right? In this case also it is scattering state. In earlier case, so it can escape in only one region. Here it can escape in both regions. That's why I have written like this. If E is greater than V at plus infinity or E is greater than V at minus infinity or both. This is both, isn't it? It can escape. Then it's a scattering state. This kind of question exists, okay? So what will happen is our potential goes to 0 at infinity actually, okay? Suppose if you take your Dirac function value, am I right? Isn't it? Minus alpha delta of x, am I right? Our v of x goes to 0 here, isn't it? If v of x is 0, if v of x is 0 and if it satisfies this condition, okay? If v of x is 0 at plus infinity as well as minus infinity, okay? And if it satisfies that condition, then what is the bound state situation? Isn't it? E is less than potential at plus infinity or minus infinity. This was the bound state. Are you getting my point? So that's why. So in this situation, if E is greater than 0, then what is that one? Scattering state. That's what given in Griffiths. So look at here. If potential at plus infinity as well as minus infinity is 0, okay? And if the energy satisfies this condition, then this would happen, am I right? This is a bound state then, because this is nothing but E at V at plus or minus infinity, am I right? This is nothing but E is greater than V at plus or minus infinity. So this is scattering state. This is bound state. So this was the situation. Scattering state, bound state. In case of Dirac function well, okay? Observe that one. Now there are many questions on this one. Which is scattering state? Which is bound state? You should be able to answer these kind of questions. Okay? So read Jatili, chapter 4, I think page number 216. Okay? Chapter 4, beginning part. Okay? Very beginning part. So in case of bound state, we will have discrete energy actually. Okay? Isn't it? Particle in a box, particle in harmonic oscillator. In case of bound state, we will have discrete energy. In case of scattering state, there is no bound, what you call discreteness of energy. In case of free particle, we have seen, am I right? That's what you need to find, okay? If energy is discrete, like in case of particle in a box, particle in harmonic oscillator, we call that one as discrete spectrum. Actually, that energy eigenvalue is called a spectrum. New word. Not our, what you call spectrum, whatever we observe after prism or something, okay? Spectral line, okay? Energy eigenvalues are also called a spectrum actually. Energy eigenvalues are also called a spectrum.
Atomic spectra.
No, not atomic spectra. That is a transition emitted photon lines. I'm talking about energy eigenvalues. They are called a spectrum, okay? H psi is equal to E psi, am I right? H cap psi is equal to E into psi, am I right? These energies are called a spectrum. Is that okay? Quite strange word, isn't it? Okay? If energies are discrete, we call it as discrete spectrum. Okay? If energy values are continuous, in case of just like in case of particles, free particle, we call it as continuous spectrum. Okay? These energy eigenvalues, these are called a spectrum. Okay? Now we say this one have this will allow only continuous spectrum, am I right? Always scattering state, am I right? So now in this situation earlier, isn't it? This will allow some what you call discrete spectrum, some what you call continuous spectrum, am I right? Some bound states are there. Bound states are discrete spectrum. Okay, scattering states are continuous spectrum. No boundary for energy for scattering state. Yeah, speak out.
So can I take some example like this?
No, again, free particle is the one of the example.
Alpha particle, like
If you which alpha particle?
I mean, if I will take alpha particle.
This is not alpha particle situation. It is going to infinity here. In the alpha particle situation, it is rising and it is lowering. You have another classically allowed region. Here only classically allowed region was this one actually for this energy. Okay, observe the difference. Now what I am saying is, if energy is like this, okay, if energy is like this, so it will allow discrete spectrum, bound state which are discrete eigenvalue. It will give discrete eigenvalue. If energy is greater than this value, what will happen? Let me call this one as V0. Okay, if energy is greater than V0, then what will happen? It will be scattering state. It will have continuous spectrum. That means continuous eigenvalue. Is that okay? So this will allow mixed spectrum. We say like that: discrete spectrum as well as continuous spectrum. This will allow only continuous spectrum. This will allow only discrete spectrum. Which one? Your harmonic oscillators. Isn't it? Whatever the energy you take, bound. Am I right? This will allow only discrete spectrum. Isn't it? So particle in infinite square well. This will allow only discrete spectrum. But this kind of potential will allow mixed spectrum. Mixed means for some energy, if energy is less than V0, okay, it will have discrete eigenvalues. If energy is greater than V0, that's a scattering state, it will have continuous energy eigenvalue, continuous spectrum. Okay, you need to observe all of this and you need to make a list actually. Okay, which is mixed spectrum, which is continuous spectrum. Okay, you should read chapter 4, 1, 2, 3, 4th page, up to 4th page, okay? Yeah, I'll mention this one as a reading assignment. Yes, tell me. Yes, tell me.